It's not really CO2 that's doing a lot for climate. It's clouds. Clouds make a very big difference to climate change.
My guest today is Robert Ian Holmes from Australia.
I left school at 16 and mostly worked for myself, but had quite a few different jobs until I got into my 50s. I did a degree in astronomy first, and then I did a degree in mining engineering, and then I did a master's in environmental engineering. Finally, just recently, a PhD in climate science / mitigation. I didn't think I'd do that after the master's. It was quite difficult, but anyway, we got through it, and here we are.
What was it like being a student in climate science as a climate skeptic? Was that a hard thing to do?
Yeah, quite difficult. Because I got the mining engineering degree, I went into underground coal mining, and I was working there for a few years. And I did some work on cutting greenhouse gas emissions. It wasn't really part of my job. I just did it for something to do, a bit of extra work. Soon after that, the climate tax came in. This is 2012. I did go to a conference in Colorado, actually, as part of that, as part of the PhD, and presented a conference there, how to cut greenhouse gas emissions from underground coal mines. That was part of it. I was always interested for a long time in the climate change and greenhouse gases and so on, and trying to work it all out. It's a large and complicated field, as you know. In the end, I recently published some papers on climate change, greenhouse gases, and so on. There's 3 recent ones starting in 2017, which we'll get to later on. But anyway, as my slide here says, my PowerPoint slide, hoping to bring reason and some empirical science into the climate debate. That's what I'm hoping to do. A lot of it seems to be modeling, and people just don't get it. How can you predict the climate in 100 years' time? It just, for a lot of people, it doesn't add up when it's difficult to predict weather, for example, a week in front. This is just my personal opinion, but science and reason has been abandoned, forces are lying. Some are convinced that the danger of a climate catastrophe is so great that not only is it reasonable to dispense with the scientific method, but with reason and decency as well. We've seen a lot of evidence of that. But I believe that the opposite is true. If the potential danger is so great, then the scientific method must be adhered to even more rigorously. Only then will we have the knowledge to be able to follow the correct course of action. We'll just go into climate cycles to start with, because although it's not in any IPCC report, the climate for both past and present is dominated by climate cycles. I've identified 16 main ones. Unfortunately, the only climate cycle that they have in any IPCC reports is the Schwa. Of course, they say that it has basically no effect. It goes up and down and doesn't really have any effect long-term on long-term climate change. It increases the temperature over the 11-year cycle by maybe 0.05 degrees and then down again the same. So it has no net effect on climate change. There's other climate cycles that are much more important to us at the moment when we're considering climate change and global warming and so on. And the problem is the IPCC does not recognize any of these climate cycles, as I said, except one, the Schwab. But they're definitely there. Now, this is the Atlantic multi-decadal oscillation. This is how the oceans warm and cool, mostly in the northern Atlantic. And 1880 was a warming, 1910 a cooling, 1940s a warming, and now we're in the warming cycle again. This is obviously a climate cycle, and it's the Yoshimura climate cycle, 60 to 62-year Yoshimura. They took data from the last 100 years from all the stations in all these countries. So it's a worldwide temperature graph. But because they've taken only ocean ice sheltered thermometer stations, it shows no effect from the oceans, which have been warming. So this temperature graph shows us that the land is not really warming at all. again, we see this 60-year Yoshimura climate cycle, and in it the Schwab as well. They seem to be getting rid of these climate cycles, which are still in the Hadkrut 3 data, which does end a little bit, before the present time because they stopped, moved to Hadkrut 4 and Hadkrut 5. Here we've got the Hadkrut 4. This is a 50-year annual trend. So instead of having a yearly trend, if you turn it into a 50-year trend, it reveals underlying climate cycles. This is again the 60-year climate cycle we've been talking about. This Hadkrut 4 from the Arctic, usually when, I'll call them CO2 proponents, when the CO2 proponents show you a chart, they started in the 1970s here. They only show you the warming part, but they ignore the past where it's been as warm or warmer in the Arctic as it is now. So as you see here from the Hadkrut 4 chart going back to 1920, you'll see that it was warm in the 1930s and 40s, as warm as now, if not warmer. Again, we're seeing that 60-year climate cycle very prominent in the data. Longer term, it should go back 1,000 years. We see the bond cycle. So it peaked in about 1100, and it's peaking again now in 2000. So this is a 1,000-year bond cycle. In between, we have other climate cycles, which is this 240-year, roughly, Swiss climate cycle is there in there as well. If we look at the last 1,000 years of non-tree ring proxy data, we're going back beyond the thermometer record now. This is work by Null in 2007, which showed the last 2,000 years. Here we'll start about AD 0, and then we've got the Dark Ages, which was cooler. We've got the medieval warm period, and then we've got the Little Ice Age, and what I'll call the current warming period. This is again the 1,000-year bond cycle, very prominent in the data. Now, this temperature reconstruction goes back about 2,500 years. This one's from China. So you can see that these climate cycles were worldwide. The CO2 proponents are always saying, this was just in the North Atlantic or something, or the Northern Hemisphere or the Southern Hemisphere. They say that these climate cycles were just local, but they were actually worldwide. Here again, we've got the 1,000-year bond cycle and the other shorter-term cycles in between. This is from Lou 2011. He's expecting a fall in temperature, slight fall, not a severe fall in temperature until the year 2068, and then a rise again. Okay, going back a bit further, we're going back 10,000 years now. We see longer climate cycles begin to emerge. The 2,300-year Bray climate cycle. Go back a lot further. So if we go back 5 billion years, that's what we see in the last million or years or so. We see 100,000-year cycles of ice ages, going in and out of ice ages severely for the last 100,000 years. You talk about climate changes, that's real climate change. That is, it's not like what's happening now, which is nothing compared to that. You got the range in temperature of 10 degrees from warming to cooling. Where we are is about here. For the last million years, you had a 41,000-year climate cycle. This comes from sediment cores. Over the last 500 million years, and here is found that there's a 32 million year climate cycle. They all piggyback on each other. What's the cause of this 32 million year climate cycle? Is that the solar system orbits the Milky Way once every 250 million years, as you probably know, but also at the same time it goes up and down through the disk of the Milky Way, like a dolphin, I suppose, every 32 million years. It causes cooling and warming periods in the Earth's climate on the 32 million year cycle. This is to do with clouds, and we'll come to that. It's cosmic rays causing clouds. So when you get more cosmic rays, you get more clouds, you get a cooler climate. You get less cosmic rays, you get less clouds, you get a warming climate, which is what we've got now. Going back further, 500 million years here, again, on these time scales, there's no relationship between CO2 really and temperature. And here you can see the large scale climate cycles we're talking about. You get ice ages, and these are related to the passage of the solar system through spiral arms. So it's a 140 million year cycle. So when the solar system goes through a spiral arm, that causes cooling. Now, we're in an ice age now, and we're in the Orion spiral arm segment. We're passing through that right now, and that has caused the climate to cool. That's why we're in the present ice age. Okay, now we'll look at a bit of data about CO2, which shows that there's no warming from CO2. This is a paper published by Clark and Iacana, and they took measurements from the atmosphere. This is the important part here. That's in the troposphere. That's 10 kilopascals pressure. So this bottom part of the graph is the troposphere. And in the absorption emission spectrum for CO2, you see there's no effect. But there is, from more CO2, there is warming higher up in the atmosphere. In the mesosphere and the stratosphere, there's warming. But in the troposphere, there's nothing. There's no effect. All the models, all the computer projections said that there must be a hotspot. A hotspot must develop over the tropics at about 12 kilometers in height. So in the upper troposphere, the troposphere is about 18 kilometers high in the tropics. What this is, it's a slice through the atmosphere from the North Pole to the South Pole, and going upwards. This is over the troposphere here. That's the equator. So all these models, if CO2 greenhouse warming exists, there must be a hotspot developing. But this is the data. This is measurements of the atmosphere after a lot of CO2 has gone into the atmosphere, anthropogenic CO2. So these weather balloons have measured the temperature, and it's completely flat. So greenhouse gas theory says that there must be a hotspot over the tropics, and there also must be warming at each pole. But this is the data, and it shows there's been warming in the Arctic, no hotspot over the tropics, and cooling in the Antarctic. Historically, CO2 has lagged any change in temperature. So if you look at the ice core proxies, temperature changes, and then about 800 years later, CO2 changes. When the climate cools, CO2 follows it down 700 years later. There's also an effect on shorter time scales. This graph is a recent one, as you see here from the date. It shows that in blue here, we've got the ocean temperature changing slightly. And the green is CO2, which again is following. In this case, it's following 11 months later. There's a slight change in ocean temperatures, and then there's a slight change in the amount of CO2 in the atmosphere. This is to do with Henry's law. When the oceans get warmer, they release CO2. When they get cooler, they absorb CO2. So again, it's CO2 is not the driver, it's the effect. Most of the warming in that warming Earth is the ocean warming. The atmosphere is relatively small and follows on from the oceans. There's a problem here for the greenhouse effect because they said that the warming is coming from CO2. According to the IPCC, it's 98%. 98% of all warming since 1750 and climate changes, 98% is supposed to be coming from greenhouse gases. The greenhouse effect, according to the IPCC, that's what their attribution states from their working group 1. Now, there's a problem there because radiation from CO2 in the atmosphere, long-wave radiation, cannot penetrate the ocean, so it cannot heat the oceans. This is the main emission band for CO2. It's about 15 microns. And this shows the absorption of water of the ocean to radiation. Down here is where the oceans are heated by shortwave radiation from the sun. So shortwave radiation from the sun can penetrate the oceans, as you say, down to, I don't know, hundreds of meters. But longwave radiation from CO2 cannot penetrate the ocean. It's only a few microns. It's just touching the surface. So that's more likely to cause cooling than warming the oceans because it will cause evaporation. So that doesn't work. Now, when you compare the planets, you got Venus, Earth, and Mars here, for example. Now, the CO2 absorption bands between the three planets are very similar, despite the obvious differences in CO2 levels. So you got 96% CO2 in the Venus atmosphere, 95% in Mars, and only 0.04% CO2 on Earth. And even if you count all greenhouse gases on Earth, it's only 2.5%. We have a dearth of greenhouse gases on Earth, and yet the absorption bands from all three planets are the same, very similar. So this means that the absorption band for CO2 on Earth is already saturated. So you can't get any more warming basically from adding CO2 to the atmosphere. We'll have a look at CO2 now, CO2 levels. This is a graph which shows GISP2, the proxy for temperature from Greenland, over the last 11,000 years, as you see there. So this is really the entire Holocene. So the early Holocene was very warm, as you see here, and it started to cool about 3,000 years ago. And we've got the climate cycles, like I was speaking. You've got the 1,000-year bond cycle, the Minoan warm period there. We got the Roman warm period, the medieval warm period, and the current warm period. And here we've got atmospheric CO2 from the Empirical sea ice core. No correlation at all. In fact, it's the opposite. That's according to the ice core CO2 record. There are problems with that, and we'll come back to that. Plants lose CO2 because CO2 is plant food. So you give rice, for example, more CO2, grows better. Current levels about here, rice is growing pretty well, but you double the CO2 level, they grow even better. And the same with most plants. This is another one here. This is Dr. Ritsu with his son, did a bit of research into this some time ago. That's at ambient levels of CO2. This is showing a Christmas tree growing. With 150 parts per million extra CO2, the tree grows better. With 300 parts per million extra, grows even better. With 450 parts per million extra, basically doubling what we've got now, grows even better than ever. Grows twice as high as it does with ambient CO2. So CO2 historically has never been bad for life. So it's when you look back over historical periods, CO2 is about the lowest now it's ever been in the Earth's history. It's pretty close to an extreme low. So why someone should fear the level of CO2 being a little bit higher, I'm not quite sure. It seems to be, widespread. The CSI recently published a paper. It was Donahue that works there, and he found that the Earth is greening due to the extra CO2 in the atmosphere, which we humans have probably put a lot of it up there. But the question is it a bad thing or a good thing? How bad are the bad things associated with it, and how good are the good things associated with it? Well, CO2 fertilization has caused the deserts to green in places, particularly in southern fringe of the Sahara there. You've had a lot of new plant growth, and the extra plant growth for crops has meant that you could feed 500 million more people just through CO2 fertilization. So I think that's a good thing. There is a problem with the ice core CO2, and when you compare it to other proxy CO2 data, such as from plant stomata, there's differences I'll explain. First we'll just have a look at this. The CO2 proponents always say, the CO2 level is high. It's higher than it's been for millions of years. They often say that, but they're relying on the ice core CO2 data exclusively. Now, if you look at other proxies for CO2, for example, here from Kuenberg's 2004 PhD thesis. He'd found that using plant stomata, the CO2 levels was actually as high or higher than now, just 1,500 years ago. That's the present, and that's 500 AD. So the one problem is with universities is that they don't like you to say the wrong thing. So Kuenberg, before he got his PhD thesis approved, he had to cut the chart off here and discard this data. It was deemed to be inconvenient. These dots here are the CO2 ice core data. They're approved. You can publish that, but when you publish something like this, it's not approved. Here we've got a paper by Steins daughter published in 2013. It directly compares the ice core CO2 data with other proxy CO2 data from plants. Here you've got the ice core. If you notice the scale, the range of the ice core data over this period, which is 14,000 to 11,000 years before present. So it spans about 3,000 years, this proxy data. The range of the ice core data is only 20 parts per million, as you'll see from the scale. But the plant stomata range is, if you look at the scale, is much greater. It's about 245 parts per million, the range from the high to the low. With plant stomata CO2 says that the CO2 is going up and down enormously, but the ice core proxy data says no, CO2 is low and monotonic, flat. So there's a big difference there. So we have to think, oh, well, why is that the case? It's due to the constant diffusion effect. So once the CO2 goes into the fur, into the ice, it gets snowpack on top of it, it gets compressed. That compression causes a change in the CO2 that's in the ice. Once it gets under an enormous amount of pressure, the more pressure it gets under, the more problem you've got. You get a flatter and a lower CO2 level than you do from other CO2 proxy data. We'll have a look at cosmoclimatology. It was Henrik Svensmark who was mainly doing this. Satellite data, you at UNHMSU, just from 1979 to the present, you'll see a slightly rising temperature graph. At the same time, you've got global cloud cover, and it fell about 2% over the globe over this period, the same period. So when you got less cloud cover, you get higher temperatures. It's very logical, really. More solar energy hitting the ground and oceans, heating them. And so you get warming. If you got more cloud, you'll get a cooler climate. This is basically what Svensmark said. So it's not really CO2 that's doing a lot for climate. It's clouds. Clouds make a very big difference to climate change, to climate temperatures and climate change. And they have a lot to do with climate cycles as well. Where's the evidence? This plot is a total cloud cover versus global surface air temperatures. So the plot clearly shows that when you get more cloud cover, you get cooler global temperatures. So it's temperatures on this cloud cover across the bottom. And what this is, it's around about 0.06 degrees centigrade for every 1% change in cloud cover. Now, between 1980 and the year 2002, temperatures went up about 0.4 degrees centigrade according to global temperature data. But at the same time, low tropical cloud fell by 6%. So 6 times 0.06%, that's about the entire temperature rise that we experienced in the late 20th century. It can be attributed to cloud changes. For example, here. Okay, so we've got global surface temperatures here. This is Hadkrut 3, slow rise from the 80s, early 80s to the 2000s, and then flat. cloud cover. This is tropical cloud cover, low cloud cover. You've got a big fall in cloud cover over that period from around about 67% down to about 60%, which has caused this warming. That warming was caused by the falling tropical cloud cover. And then the cloud cover was flat after that, setting the temperatures. No need for CO2. Now, we'll get back to cosmic climatology, which is to do with cosmic rays impacting the Earth's climate via cloud changes. So it's not just that there's more or less cloud due to cosmic ray changes, cosmic ray flux changes. It impacts albedo as well as having less cloud cover and more sunshine. So, for example, in the late 20th century, you've got less solar activity. So the CO2 proponents say, oh, well, it can't be the sun. You can't have warming from the sun when there's less solar activity. But of course you can. If there's less clouds, then you get more solar energy to the surface, to the oceans and the land, even if the solar activity is a little bit less. So you can get warming from the sun when there's less solar activity. It depends on the cloud cover changes. So that's something that they sort of forget about. Now, what these cosmic rays are, well, most of them are protons. So the relativistic protons coming in at high velocity generally from outside the solar system, from events such as supernova and so on, cosmic events. Now, it's the high energy protons. When they hit the upper atmosphere, they cause a shower of muons right through the atmosphere, right to the surface. And these can cause cloud generation. So they can create clouds. So you get more cosmic rays of the right intensity or right strength. Then you can get more clouds and so on, or less clouds depending on the intensity of the cosmic rays. So, and you can see the dates here. And there's a strong correlation, causative correlation between changes in cosmic rays and cloud generation, so and temperatures. In this graph, the effects of volcanoes and El Niños have been removed. So there's an excellent correlation between global temperatures and cosmic rays. In the case of cosmic rays, it's causative relationship. So the cosmic rays cause changes in clouds, that cause changes in temperatures and climate. Whereas CO2, as you know, is the opposite. It's always in effect, it doesn't cause anything. Okay, here we've got more work by Kirkby in 2002, which shows the galactic cosmic ray flux falling. Now, the coldest temperature in the whole Holocene in the last 10,000 years was the Little Ice Age. And see, the peak of the low in the Little Ice Age was in 1690, which is up here. This graph is inverted. So that was the coldest temperature when you got the most galactic cosmic rays impacting on Earth because they were generating more cloud. Here you've got climate cycles appearing again in this. As the sun changed its intensity, the sun causes a few of these climate cycles. It changes the cosmic ray flux that impacts the Earth because the sun pushes the cosmic rays away, and when the sun is stronger and the sun is weaker, it lets more cosmic rays impact the Earth, and so the Earth's climate cools. As you can see, the last 100 years has been a strong fall in the galactic cosmic ray flux. And this is because solar activity has increased. Over the late 20th century was the strongest solar activity for thousands of years, but we'll come back to that. The sunspot, which is a proxy of solar activity, determines your cosmic ray count, or how much cosmic rays impact the Earth, and how that changes the cloud color. So really, it's clouds that are driving a lot of climate changes. Here we've got proxy cosmic ray flux and proxy temperatures. So the oxygen-18 isotopes are proxy for temperature, and the carbon-14 isotopes are proxy for solar activity really in cosmic ray flux. And of course, it's the CRF, the solar activity, that is driving the temperature on Earth, not vice versa. The temperature on Earth can't drive solar activity. Now, just expanding on that theme a little bit, going back about 60 million years, we got the Eocene optimum here about 50 million years ago, and then the climate cooled. Then we had the Antarctic glaciation. That was about 33 million years ago, and the Antarctic first. Before that, there was no ice at either pole throughout this entire period. The Earth was much warmer than it is now. Now, this just didn't happen as an accident, and it was nothing to do with CO2. It was the cosmic rays, as I said, and the solar system's passage through these spiral lines of the Milky Way, which causes more cosmic rays, because the spiral lines are density waves that move around the Milky Way, and those density waves compress gas clouds and cause starbursts. So you get a lot of new stars forming, thousands of new stars forming. High mass stars go supernova pretty quickly, only last a few million years, and then they go supernova, and you get a burst of cosmic rays, high intensity cosmic rays, exactly the sort of cosmic rays that bypass the sun trying to keep them away, and cause ice ages on Earth and cooling on Earth. So this is what you have here. So the Antarctic cooled about 30 odd million years ago, and then it thawed, it got warmer. And then about 15 million years ago, the Antarctic reglaciated. But this was a starburst, a very strong starburst. It correlates with that strong about 15 million years ago. And then the climate cooled again. 3 million years ago, we had another powerful starburst, which sent us into the current ice age. And this is where we are now, down here. Very, very cold. The last 3 million years, the Earth has been very, very cold, far colder than it's been for a long, long time. So to feel 1 or 2 degrees of warming is a little bit strange, to say the least. It shows that starbursts correlate with proxy records, the ice ages and climate changes on Earth. So, but the Aris effect really is a strong negative feedback in evidence. How do we know that? When the outgoing radiation falls, when the Aris closes, that causes less outgoing long-wave radiation, and causes the climate to warm. But once the climate has warmed quite a bit, that causes the iris to open again and let the long-wave radiation out. You can see it just there. It's a strong negative feedback. So the climate, this warming and cooling, is controlled by this outgoing, really by the Aris effect. The CO2 proponents always show this type of graph. They say, oh, well, shortwave radiation comes in from the sun and the Earth emits long-wave radiation. This type of graph is very misleading because it shows that the sun has no long-wave radiation. That's just not true. Our atmosphere is thermalized by long-wave radiation from the sun as well as from the Earth. So as well as upwelling long-wave radiation, we've got downwelling long-wave radiation coming directly from the sun. So this graph is very misleading. This is a more accurate graph, which shows the solar black body radiation totally encompasses the Earth's black body radiation. So the sun has far more long-wave radiation coming from it than Earth has, but they don't show that. So we've got long-wave radiation coming down from the sun that already thermalizes the Earth's atmosphere and all the greenhouse gases. So you get them totally restricting their increase in their activity. So it's a little bit misleading to say that the sun is shortwave and the Earth is longwave. No, the sun is all wavelengths, longwave and shortwave. A little bit about the poles. The current snow cover last year was massive. There's no reduction in snow cover at all. So this is a record of snow cover kept by Rutgers University from the early 70s, and basically it's flat. The minimum is really flat, but it does vary a little bit. It could have a little bit to do with black carbon. So if you've got a lot of power stations like they have in China putting out black carbon aerosols, that could cause a bit of temporary melting of snow, but it's not permanent. Once those power stations have been replaced by modern power stations, there shouldn't be a problem there with the black carbon. CO2 itself doesn't really do anything. It's a Hadkrug 4 Arctic temperature graph, which shows it was just as warm in the 30s and 40s as it is right now. So it's just a cycle. This is Greenland temperatures, just normal climate cycles. The Antarctic, if you've got global warming, it doesn't have to be the whole globe, but the Antarctic hasn't warmed. Apart from the science of climate, there's also the economic side of climate science. Will warming be a benefit, or will it be something bad for the economy? Well, according to Professor Toll, who published this data from his paper in 2009, he calculated there's a net economic benefit to warming up to 2.2 degrees centigrade. So that's the economic benefit, and that's an economic loss once it gets over 2.2 centigrade. But that temperature is from current levels. So from 2009 levels. So according to the IPCC, it's been warming since 1750 due to CO2, 0.8 degrees. So when you add that to this, it's 3 degrees centigrade. So there's a net economic benefit up to the IPCC level of 3 degrees centigrade of warming, which we're very far from. Even according to them, it's only 0.8 degrees. When look at the sun, the TSI from the sun and short-term climate cycles, you can see that it was warm in the late 1700s, and it cooled to about 1900, and then it's warmed again now. So this is a climate cycle. All the cities show the same V-shaped cooling and warming. And this is the Swiss climate cycle, 248 year-long cycle. So Ledecky identified these 5 climate cycles from the data. Most prominent one is that one, the 248 Swiss climate cycle. The 80-year Gleisberg and the 61-year Yoshimura, these are shorter-term climate cycles. And when he fitted the climate cycles to the data, he got an exact match. It's no warming from CO2. Neptune warming and brightening. This is Earth's mean temperature anomaly, and this is TSI. As you can see, they correlate with each other fairly well. So, and we've got similar things happening on Pluto. So the planets are experiencing global warming as well. Now here we've got this. This is quite important. During the Earth's orbit of the Sun, the orbit is slightly elliptical, so it's not circular. You get different levels of TSI during the year as the Earth orbits the Sun, of course, because we're slightly further from the Sun in June and July, the northern summer, and in the southern summer, sort of December, January, we're a little bit closer. The difference in TSI is quite big. It's about 90 watts per square meter top of atmosphere. And on the surface, it's 15 watts per square meter. That is an enormous change. It's actually 1,000 times more than the alleged change in forcing from CO2. But this is over a 6-month time period. So the forcing changes naturally. This is due to the eccentricity. Between July and January, you get that 15 watts per square meter extra at the Earth's surface. But from CO2, they're alleging 2 watts per square meter since 1750. So 270 years, you can see the difference there. So natural climate, natural forcings just that one natural forcing is 1,000 times greater than the alleged CO2 forcing. And yet the Earth temperature doesn't change radically over that 6 months. Why not? Well, it's because of clouds. Again, it's negative feedback. He showed that between the northern and southern hemisphere, the eccentricity, although it's a very big change in TSI at the surface over just a 6 months period, makes no difference to the global temperatures or because the clouds make up for it. If the clouds can make up for 15 watts per square meter over a 6 months period, they can make up for a lot more than that if CO2 does cause any forcing. What it did in this paper was it took the solar cycles from solar cycles 1 to 8, which are these ones in red, shifted them forward 211 years, and they match up pretty well with the current solar cycles. These ones in black are the current solar cycle. We've got the strongest one in 1960. As I said, the late 20th century, which is these 5 solar cycles here, that was the strongest solar activity for thousands of years. If you're talking about the cause of warming, that would be a real cause of warming. Anyway, what I found was that these first 8 climate cycles match up pretty well to the current ones, which tells you that this might be just, again, a cycle, but a longer term cycle that's happening with the TSI changes over the Schwab. So you can even predict slightly. Prediction's difficult, but you can say, well, we might have a bit of cooling over the next 30, 40 years. This is a paper by Ledecky in 2011, which shows the sunspot numbers over the last 2,000 years. Obviously, this is proxy data, so you got a slow reduction in sunspot numbers until you get to the late 1600s, when there was 0 sunspot numbers for a couple of decades, not visible on the sun at all. So that was a solar minimum. Then you got a sudden massive increase in solar activity since basically 1700. So over the last 330 years, we've had a massive increase in solar activity. The current solar activity is the highest for 11,000 years. This graph, as you see, goes back 11,000 years. So the last similar solar maximum to what we've got now was 11,000 years ago. It was a grand maximum, and now we have we had a grand minimum in the Little Ice Age. More evidence that solar activity has climbed enormously since the late 1600s, which was the peak of the Little Ice Age. This is work by Semi in 2009, which shows the inverted scale of orbital angular momentum of the planets and the sun. Again, we see in this data climate cycles. You got the 1,000-year bond climate cycle. I think it's now 134 years, but we'll call it 1,000. So that's the current time there. This is the year, just after the year 2000. That's where we are. This is inverted. So when it goes up, that's cooling, and when it goes down, that's warming. So remember, this is a 1,000-year cycle and bond cycle, and in between we've got all these shorter cycles. Mostly prominent here is the Yoshimura 61-year solar cycle. So we're right at the peak now. This is an inverted graph. So we're right at the peak of the warming now. The peak of the cooling was here in 1690, the coldest in the last 10,000 years. Now we've got a warm period, but it's definitely not the warmest in the last 10,000 years, but it's warmer than it's been for about 300 years. So we've had global warming since 1690. So for the last 330 years, we've had global warming, the natural period of global warming. Several major solar cycles, climate cycles, sort of mixed up together and showing why we're where we are now. This is where we are now, just after the year 2020 there, about here. and we're following this graph. That's minimum temperatures here in the late 1600s and warming to where we are now. It's going to keep generally about the same direction. Why it's warmed over the last 100 years is due to the underpinning by the eddy cycle and the Bray, the longer term Bray cycle, eddy cycle, or bond cycle, some people call it. All these climate cycles piggyback on each other. Where we had the underlying warming trend the last few hundred years is because of these longer term underlying climate cycles. We've got roughly, from the greenhouse gases, we've got roughly 2 watts, just over 2 watts per square metre since 1750. Now, they say that the solar irradiance plus all natural climate changes are just down here in this little tiny bit, you can hardly see. That's 0.05 watts per square metre since 1750. Why so small? Why is that so tiny? We'll come to that. The proponents also claim that 2,000 top scientists worked on the IPCC's reports. Well, the only scientists who matter are those who work on Working Group 1, which deals with attribution. What caused the global warming we're experiencing now? In AO5, there's 255 of them who worked in Working Group 1, but only 18 of them worked on attribution. In other words, the whole IPCC document report rests on these 18 people, not thousands, 18. And several of them were students at the time. 3 of them were still students at the time the report was made. And many of them, because of the political nature of the IPCC, many of them were chosen from third world countries, not for their long experience in climate science. So just a handful of climate scientists, maybe half a dozen, determined the IPCC report from start to finish, because attribution is everything. Attribution determines climate sensitivity, and that determines all the working groups 1, 2, and 3, what happens going through. This is another reconstruction that the IPCC doesn't use. They said, from 1750 to now, there's been no change in TSI. They're not far from being accurate, but they're ignoring all this. Look at the range. So the peak low is about, let's say, 1353, peak high 1363. So you've got at least 10 watts per square metre of TSI range here. But the IPCC said, no, it's only 1.5 watts per square metre range in TSI, because they're ignoring all this past data. This is another proxy TSI from someone else instead, which shows something similar to the last graph. It could have a 1700, but I don't think that's deliberate. 1690 was even lower, about 1354 watts per square metre. So if you start from 1354 and go to the present, you've got at least 7 watts per square metre of rise. And that is a lot. It's definitely more than any alleged CO2 promising. Makes a big difference, because the temperature rise from 1690 to 1750 was far steeper and higher than anything we've seen today. It was because of this massive rise in TSI over that short time period. This is beryllium-10 isotope, which is a solar flux proxy, and we're going back 300 years here. As you can see, solar activity was very low, as you see, around 1700. Then 1750 was quite reasonable, and then a slow increase, you could say, with variations over time since then. But the biggest increase was from 1700 to about 1750, 60 in solar activity. So you could say starting from 1750 is kind of a cherry pick, really. Then we've got temperature adjustments and hockey sticks. So the third assessment report from the IPCC, man's hockey stick. It's been cold since then. He reconstructed temperature over the last 1,000 years using tree ring proxies, which are not a very accurate method of finding a temperature. because other things cause trees to grow and to not grow rather than temperature. And then on the end is tacked on this current data. So it's a no-no in science. You don't really tack on thermometer data to proxy data. It's, if you do that, you should really emphasize it, but you shouldn't really do it at all. What's wrong with tree ring data? Now, this is someone else did this work in the decade 2011. It shows proxy tree ring data in green over the last 2,000 years. You can see much more variability in the other proxy data than the tree ring data. So tree ring data are a bit suspect, just like the CO2 ice core data is suspect. And talking about suspects, this is work by Tony Heller. This is the BOM data, Bureau of Meteorology data from Australia. That's the entire record unadjusted. It was hot, very hot in the 1860s to 1900 period, hotter than the present. Extensive bushfires, for example, huge heat waves in the late 1800s. The fires were so intense in Victoria at that time that the stuff from the fires, the ash was falling on New Zealand. That's how intense the fires were. But this is the data that the Bureau of Meteorology sent to the global network of records. They cut it off in 1910. That's here. So they cut out all this warm period and sent the data only from 1910 to the present, which does show a warming. It does show warming from 19, slight warming from 1910 to now. But then in orange, they adjusted the data and gave it more warming. So they more than doubled the warming that wasn't there in the original data. There was no warming. In fact, there was probably a cooling in the original data. That's probably the last graph I was showing you. Other people responsible for collecting global temperature data, such as GIS, have adjusted their data. These adjustments are now being monitored, but they've only really been monitored since 1999. So what they did before that, we're not quite sure. Probably something similar. But what the effect of the adjustments has done to GIS, it's cooled the past and it's eliminated any climate variability. Natural climate cycles, they've been eliminated, and the later periods have been warm. So it's created a smoother, steeper temperature graph, which more accurately matches the CO2 data. Here, I've put in the UH6, the satellite, the entire University of Alabama at Huntsville satellite data in green. You can see that the GIS temperature data is several times more warmer than it should be compared to the satellite data. NCDC, we've got the same story. Climate variability has been eliminated, so the warming of the 1880 periods was cooled. Basically everything before 1940 has been cooled to make the graph steeper. And then the 1940s period was changed as well. And later data has been warmed again to create a steeper graph. And Hadkrut have done the same thing. All of the periods basically have been warmed. So they've smoothed the data and increased the steepness of the graph. Okay, this is data from the oceans by Goretsky, 2012. The ocean data. It was warm in 1880, cool in 1910, warm in 1940, cool in the 70s, and warm now. And the surface shows less change than the near surface, but it was the warming from 1910 in the oceans to the 1940s. It's very similar to the warming from 1975 to the current time. So. And yet the IPCC say the last warming was caused by CO2 and the first warming wasn't. The deep ocean was warming far more from 1900 to 1940s than it has been doing recently. Here again, you can see the 60-year climate cycle, very prominent. And also underlying it, you can see, well, you can't on this scale, but on other graphs, you can see the underlying longer-term climate cycles. to Scotland temperatures for the last 800 years, so going back to the year 1200. This is obviously a reconstructed proxy. So you can see climate cycles in here as well, although climate cycles are less prominent in local areas than they are globally. But anyway, they're still visible. The temperatures in central England since 1659. And you just don't see any rapid increase due to greenhouse gas emissions over the last 50 years or whatever. It's just the normal climate cycles that happen everywhere. Lowy did a poll in Australia a few years ago to ask people how much are you ready to pay to stop climate change or to fight global warming. Unsurprisingly, more than 50% of people said less than $100 a year. 40% of people said nothing. There's very few people, actually, it's only 3% of people who are ready to spend $2,000 a year to stop climate change. Those numbers have been getting worse for the CO2 proponents over the years. More people unwilling to spend even a cup of coffee a year to stop climate change. The problem is that most people in Australia don't know it, but they're already spending $1,500 per family per year, whether they like it or not, due to the climate actions that the government's taken, and particularly in relation to climate taxes and energy changes. That's what it's costing. So people are in this category, whether they like it or not. The discussion really in climate is about what is the climate sensitivity? What happens if you double CO2 in the atmosphere, or the equivalent in greenhouse gases? The IPCC says you get a warming between 1.5 and 4.5 degrees centigrade, but not immediately. They say it takes place over decades or even centuries. There's a few problems with that. The paper I published in 2018 shows that there's a thermal conflict between the ideal gas law and the greenhouse effect. For the greenhouse effect to occur in a convecting atmosphere, which all atmospheres are convecting if the pressure's over 10 kPa, which means the tropospheres in planets. That's what we're talking about. So a large anomalous change must happen in the density, the pressure, or both. That's because of this formula. Why this formula disproves the greenhouse gas hypothesis, as it's presented by the IPCC, is because there's said to exist a time delay to reach equilibrium, ECS, to CO2 being in that range of 1.5 to 4.5 centigrade. The IPCC report stated that if there was a sudden doubling in the atmospheric greenhouse gas CO2, the greenhouse effect from this would operate slowly, causing an eventual 3 degrees centigrade of warming over centuries to millennia. Therefore, the claim is that the temperature would rise significantly over time with the same prevailing atmospheric concentrations, and there would be no rapid equilibration. But the ideal gas law demands that rapid equilibration. So therefore, there's a thermal conflict. There's no need to take into account the greenhouse gases in the atmosphere of those planetary bodies to calculate the temperature. For example, Venus's temperature has been measured at 339 Kelvin at 1 bar, and you can calculate that temperature from the Earth. So the temperature of Venus equals 1.1756, which is the relative solar insolation times the temperature of the Earth, and you get the temperature of Venus. So you can work out the temperature of the Venus atmosphere at 1 bar just from Earth and TSI, the two things, and vice versa. You can work out the temperature of Earth from just knowing the temperature of the Venus atmosphere at 1 bar. So through TSI, so the temperature of Earth equals 0.85 times the temperature on Venus at 1 bar 339, which equals 288 Kelvin, which is correct for the Earth temperature. Probably didn't explain that real well, but that's the paper related to it. Okay, so that's the end of my presentation.
Okay, thank you very much. That was great stuff. What do you think is going to happen to the global average temperature between now and either 2050 or 2100?
Yeah, telling the future is a bit difficult, but as you see from the climate cycles, our climate is still dominated by climate cycles, like it always was. Probably we'll see not a great deal of change. Could be a slight cooling, between now and 2050, 60, and then a slight warming after that. That's what the climate cycles say.
Okay. And where else can we find you on the internet? We can find you on Twitter at 1000 Frawley, right?
Yeah, that's right. And also the same name, you can find me on YouTube. I have quite a lot of videos on climate change there, about 100, I think. Yeah.
Very good.
My message really is that not to worry about CO2.
Thanks again for doing this.
No worries at all. Thomas, thanks a lot.